Good morning, everybody, and happy Friday. Welcome back to the production ESP32 stream, or welcome to the ESP32 production stream if it's your first time. Happy to be here. Oh, been a minute since I did these. It's been a crazy week of work and family and all that stuff. But I think I've got an interesting one for us today. We're going to be
still working in production.
hooray! That, for those that don't know, is one of the production ESP32 products I have done some work on that I have a test set up for every day for one of the companies that I consult for. So, all right. Yeah, like I was saying, I think I have an interesting one today, which is about profiling. So, as I've gotten into building products with ESP32 devices or chips in them, I'm starting to not starting to. I've realized how much. I mean, there's the code, right? There's ESP and things like that, but there's also a lot of tooling and things around just a production quality project that you don't have when you're doing Arduino or some of the other alternatives, and those are things that really help raise your operational excellence when you're building a product. And one of those things is profiling. And now there are a lot of very expensive tools. And in fact, I haven't checked the price on this recently. So let's just look up, I think it's spelled like that, Sager System View, which I believe is free for personal use, but not for commercial use. Let's see, licensing. System View, the real-time software analysis tool, which I did a stream about a while ago that has some fun, interesting things for you to look at what's going on with your product. And there is integrations for that for ESP32. Like I said, if you just search my YouTube channel, you will find information on how to set that up. And let's see, buyout licenses. I'm not seeing any. Not seeing a number here. Sega's friendly for non-commercial use. Sega's commercial use license. Here we go. Let's click on this. I swear I've seen a price on this before. PC locked, automated. I'm just trying to find a price. Restrictions, warranty and liability, miscellaneous. Ah, well, I'm not here to go through how much Sega costs, but I guess it's just a contact us. But anyway, you can buy licenses for this, but I didn't want to do that, and I wanted to, at the same time, just kind of the backstory on this, I wanted to do some form of profiling in the projects that I work on, and so I threw together a profiling utility that I want to start iterating on to kind of make to bring up to more of a production level, a la Seger's System View, but a little different. Like I said, I've used System View and it was okay, but there were some things that I wanted to tweak and use a little bit differently. So that's what we're going to be talking about today, profiling on the ESP32 and some of the things I've put together to start that I intend to continue building up. I haven't figured out how I'm going to do that for my own licensing, whether, I do want to pursue some sort of commercial use license like Sega does, also an open source like they do, and just my own spin on it. So let's go through it today as an alternative to System View from Sega. So let's come up to our project that we've been working on. And let me just come over to the chat, make sure. Ibrahim, hey, thanks for joining. Happy to have you. Okay, this is, for those that have not watched the stream before, this is just this DTF SDK playground. It is a project. Let's just go back down and cover it really quick. On GitHub, github.com/ deploy the fleet / DTF SDK playground. There we go. Okay, so deploy the fleet is a service that I've created for OTA updates. Nothing to do with what we're streaming about today here. It's a simple bare bones project that's in a Docker container. It's the way I like to do production development that has a very simple starter project that you can use to just start playing around in IDF. And so while it carries the deploy the fleet name, don't think of it as, tied to deploy the fleet here. It's just it's a it's a easy quick start that you can use sample to play around. And so that's where we're starting from. And so if we come over here to main.cpp, it's very short. You've got our app main. I've got some logging here. There was code in here to connect to deploy the fleet that I've removed because, again, we're not talking about that at all. And it just does the flash init. And then that's it. It's really flash init, and then it just logs. And so let's clear all this out and do idf.py flash monitor, and we got to turn on our device for that to work. And I'll just show you what our baseline is before we get into this here. Oh, and hopefully I might need to clean. Let's take a look. Yeah, I do need to clean. Sorry, no. Spoiler alert. Let's look ahead. idf.py full clean. Get that straightened out. Now let's do a flash monitor. Okay, so again, the baseline for what we're going to be working on today is just a while loop that prints out what the current firmware version is. That's where we're going to start. And then I'm going to show you how we're doing profiling. Undefined reference to start profiling. That is correct because we're not building it. We'll get to the start profiling. I had played around with this earlier in the week just to make sure I had all my ducks in a row for the stream, and I left it in a half-baked state here. So, okay, great. Oh, and do I have logging still messed up as well? Yes, I still have logging messed up. Okay, from our last stream, we did logging. I'll fix that in a minute as well. Let's just do that. Man, talk about preparation. Okay, let's come into component config. We're going to come down to log. Log level. Default log verbosity is info. So that should be fine. So why wasn't that printing? What am I missing up here in the code? Set log level info. All true. That should all work. We didn't print any of that out. Default log velocity is info. Maximum is that. What did we miss? Or what are we missing? Well, move this up here. Sorry, let's, because our logging is important, so we need to figure out what's going on there. To make sure that everything is working. Calling app main, which is right here. Oh, I gotta, sorry. Yes, I had wiped out, well, that could be the issue. I had wiped out my SDK config default with this profiling one, which we're going to talk about in a minute, and maybe I had lost some. Let's see what it's. Which partition? We got to figure out why we're not getting logs. Let's just force a change. Config log. Format. Oh, we messed with that. Let's turn color back on. Log level default info. That's right. Maximum. Set the verbose just to force a change in our file. Cleaning, and I might be at a loss here why we're not getting logging. That's really weird. What am I missing? at main. These are just wrappers, by the way, for ESP log I and log E. So I'm not sure why they would cause any issue. While true, yeah, where is my logging? Oh. Yeah. Okay. I know why. I really know why now. Because that's a wrapper around ESP log, I should have taken that out. But I gotta turn that on. Okay, logging, enable UART logger. There we go. That should be our fix. Okay, sorry about that. What a waste of a few minutes there. This is gonna work now. In the deploy the fleet SDK, I've got a logging wrapper that, as you just saw during menu config, you can turn logging on and off, and there we go, a lot much better. Okay, sorry, every 5 seconds we're getting that to print out. Okay, so now let's talk about how we're going to implement profiling. And so I just want to go through, I'm not going to go through all the code here. I just want to show you generally how we are achieving this. And the idea I had, this is a poor man's very cheap version of profiling. Again, Seger is a large company with a huge engineering team, I'm sure, that has built these tools over many years. This was me in like a week or less, building a quick tool for me to profile that was just really easy, that gave me the graphs that I was looking for. And let me show you what those graphs look like. We come down here. And so this is the output that we're going for. So we've got two CPUs on the ESP32, Core 0 and Core 1, and it'll show CPU usage. This is not the example that we're looking at right now. The stack low watermark. So for every thread that you turn up on your ESP32, it gets its own stack, and you can actually monitor how close you get to a stack overflow. So these graphs show that, so you can see if your thread stacks are properly sized. Internal memory, if you have PSRAM, it'll show you SPI memory statistics and how much you've got free. On this chip, there is none. And so this is what I wanted for my profiling. I just wanted to see, what does my CPU usage look like? And then when I make a change, does it get better? Just with these few little panels, I was able to find a ton of things in the projects that I work on very quickly. You just run, you see these things, and you're like, oh, that change made things worse. That change made things better. How's my stack looking? How's my free memory looking? So that's what we're going for. Oh man, my shirt there. um, that's the output that we're going for. And so what I did was I created this simple profiling thing called Runtime Profiler. And you can see it only is turned on if you've got profiling defined, and I'll show you how we do that. But this is not a lot of code. What is this? A little over 100 lines of code. That again, I'm not going to go through, but all it's doing is using the built-in IDF function calls around this, like UX task, get number of tasks. This is free RTOS stuff. Get system state, and then I'm just doing a bunch of math and saying for each interval that I'm grabbing these statistics, what's the CPU and memory and all this other stuff. And then I just, not optimized or compressed or anything. What I do is I literally just dump it out onto the console. I have a Python script. You're going to see my Rube Gold machine here, and that's what I want to improve to make this really a first class experience, because I found the tool incredibly useful. It is just a little bit complicated to set up. It just dumps out to the console raw text that I have a Python script that consumes that, turns it into JSON, and then displays it on the panel. Not in real time even, which is another thing. It just, you run it, it collects, and then you say, okay, I'm done. It closes up the file, packages up all the data, and then you display it for the web page. So let me show you what that looks like. So I've got this runtime profiler. It is the interface for it is extremely simple. There is a start profiling and a stop profiling. And it has a kconfig as well. If we come up in here into the SDK, where are we looking? Kconfig for profiling that has this very simple DTF runtime profiling sample interval. And so all this is, Ibrahim, on the, oh, not loud enough. Can you not hear me? That's max volume that I can get. Abdul Malik, sorry, just do the best you can on getting more volume on your end. So this sets the sample interval. The default is 500 milliseconds. To every, so it starts a separate profiling thread that says every interval, in this case the default's 500 milliseconds, grab stats, grab stats, grab stats, grab and dump stats. Now, what's cool about this and the things that I'm thinking about and want to do is we could be doing this in a ring buffer internally, sending it to the cloud. I do want to do a deploy the fleet first class integration on this, so that it can stream. But you know, the SDK is open source. You can grab it and see how it works and integrate it with your own tooling. But I just want to show you how I've got this, just again as a simple alternative to something like a system view. Okay, let's, what do we want to talk about next? Okay, so a couple things here. We've got a pound define of how this all works if profiling is defined. And so the way we build this, if we come back down to SDK config, well, let's come to the CMake lists first. Okay, so CMake lists, ignore this for a second because this is the additional changes, but this is what's in your default run-of-the-mill base project IDF. SDK config defaults, you're saying use sdkconfig.defaults. And this is a file I've done blog posts and videos on where you can overwrite settings in menu config that your project needs. And so you don't have to go through and manually through the UI of menu config change them. But you can string together as many of these as you want and name them whatever you want. And so all I've done at the top level CMake list is add this if the environment variable profiling is defined. Instead of setting SDK configs to just SDK config defaults, it's going to do SDK config defaults first, and then it's going to do SDK config.profiling on top of that. And so you can chain together last one wins. So if I have duplicate settings between these two, the setting and profiling is going to override any of the settings I have in defaults. And then I add this compile definition, profiling equals 1, which is what then allows all of this code, this if defined, to be true. So all that code will compile when we build our project. And so that's how we have that set up. And now let's look at what's in sdkconfig.profiling. And this is just, again, settings in menu config that you could go in and manually twiddle, but this is a much easier way to do it. And so this is just using, again, all the free RTOS stuff that's built in. Use trace facility, use stats formatting functions, vtask list include core ID that allows me to know what core a task is running on when I get those statistics, generate runtime stats, and runtime steps using ESP timer. These are just the settings that you need to have enabled for all of this to work. So you just put it in a defaults file, in this case profiling, and then I've overridden the SDK default of 500 milliseconds and set it to 1000. Okay. And did I look at that right? It's not named right. Where's my kconfig? Oh, up here in SDK. Kconfig. Okay. Every second that should update with that. All right, so now what we're gonna do, let me see what else we need to, oh, and then the only other thing we have to do, and again, I could have had this in here. I could have done pound if defined profiling, like that. Start profiling. Okay, and so the way that we will build this, I'm going to do let's see, an idf.py full clean. And then I'm going to remove my SDK config because that's how we need to rebuild it. I'm going to remove SDK config. And then what I'm going to do is I'm just going to say profiling equals 1. That's how I set the environment variable. There's many ways to do this. You could set it in the shell yourself, but this is just a simple way to do it. Profiling equals 1. Then I'm going to do idf.pybuild. Ibrahim, the y-axis of the stack is bytes free, and I'll show you that in just a second. Okay. Okay, so that built, and now let's do. I want this to be faster, so I had a command way back here. idf.py-b flash and idf.py monitor. That should just speed up the flashing. Okay, and now you can see it's dumping out every second. You see 4 seconds, 5 seconds. It's got the timestamp, and it's just a bunch of stuff. It's just dumping, 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 dumping. Perf information. Okay, so that's what's happening. I'm going to cancel out of that. And then I've got this utils folder. Sorry, utils. And then I've got a script that's called profiler. And I can show you the code for this. I don't want to go through all of it. Can't remember if this is in the repo. If not, I can put it up there. So all this is doing is opening up a serial port and reading this raw serial out and just saving it to a file. That's all it's doing. There's really nothing else happening there. It's just a fancy log storage device, and that you give a name. So I'm going to say baseline. So this is our baseline starting, and I'm going to hold the reset button on my ESP32 device so that I'm not in the middle of a run. I'm going to start. It says capturing data from device. I'm going to let that go. It's going to boot up, and it's going to start logging data every 1 second as we had it set. And we're going to let that run for a bit. Maybe a few more seconds here to just get enough data to come in. You can see it's already created a file over here, baseline perf22. It adds like a minute timestamp just to uniquely name it. Okay, now I'm gonna hit Control C, done. And let me just show you what the output of that file looks like. Like I said, it is literally just the raw output. There's no other things that are happening there other than just give it a unique name and store the log. And then, again, this is my Rube Goldberg machine where I attach all the things together. And that's what, again, this is a baseline. I do want to get this to a point of minimal integration effort and maximum value. There's another utility called log parser. And it's another Python script that then just goes through, parses that log file, translates it into JSON, dumps it in there, and then I have a web page that will display that. And so let me show you how that works. And I just pass it the name. So I'm going to do baseline perf22. I hit enter, and it's done. What it does here is it creates this perfdata.js, and then perfview.html, and perfview.js are fixed files that just use, like, I can't remember, some charting library. But if we come down here, back to our Firefox, and we hit refresh, this is what we see. Okay, so now let's talk about what we're looking at, and then we're going to do some interesting examples of how this tool is beneficial. So again, we've got 2 cores here, and it's got this dashed line is the total CPU usage. That, it's not doing anything. Printing out every 5 seconds is like no CPU usage, and that's why you see it way down here like this. And so we've got our main task, and then it'll show you every single task that's running on your ESP32. So on our core 0, we've got our profiling thread, our main thread, and IPC0. IPC0 is always going to be there. It's inter-process communication on core 0, and you'll see there's a matching one on IPC1, which is actually the only thing that is running on core 1. And so that's what our CPU usage looks like. Not very exciting. Again, Low watermark. Ibrahim, you asked, what's the y-axis here? This is the number of bytes free. So you can see our profiling thread started up here, and then it leveled down. This is the low watermark. So it's not going to go up and down. It's just how close did you come to a Stack Overflow? So on these graphs, core 1 and 2, low watermark for stack, the closer you get to 0 on these, the more in danger you are of having a Stack Overflow in one of your tasks. It's also extremely helpful because most people just put random stack values like 8K, 16K, and you'll also see if you've got way too much headroom and you're just using memory that you don't actually need. And so that's why I like these two. And then our memory. You can see we've got total free, largest free block, and low watermark. Low watermark, again, is one of those that's not going to go up and down. It's just going to show you how close you got to, how close you're getting to running out of memory. And your largest free block obviously shows you what the biggest contiguous chunk of memory is that you could allocate in a malloc call or some other fashion. Okay, so great. That's what we see. And we have, like I said, if you had PSRAM, which this particular, I'm just doing this on a dev board. I like how my shirt is like glittering right now. There's nothing to show here because there's no external RAM, but this would show if your chip, if you had that enabled in your project. So not very interesting. That's our baseline. And so now let's do something semi-interesting. Okay, so let's come back up to our code. And then all we're going to do here, now that we've got it set up and you understand how that's all working and how all the pieces run together, let's start doing some interesting things. So let's turn our connect to Wi-Fi call on. Again, this is just a simple helper utility that I have hard-coded credentials in menu config for that connects to Wi-Fi so that you have a Wi-Fi connection when you need to talk to the internet. So again, this is just a demo project, but let's take a look at it real quick. Connect to Wi-Fi is doing the code, the IDF code to connect to the Wi-Fi. And so just by connecting to Wi-Fi, let's see how things change. So I got to come back up here. I'm going to flash and monitor. We need to save main first, or else that's not going to work. And then let's take a look at how our graphs change. Okay, now we're connected to Wi-Fi, and now again we're just doing normal stuff. I'm gonna exit out of here. I just want to make sure that worked. And now let's run our profiler, and this time we're gonna call it Wi-Fi. Oops, I gotta be in the utility directory. Utils. Okay, capturing data. We're gonna restart our device. One of the cool things that would be nice to integrate with this is automatically detecting those reboots from that ETS at the top, like you can see here, Wi-Fi. This ETS and some of this other stuff. Right now I have nothing that breaks up the logs, so it'll just, if you restart it while you're capturing, it's going to do some weird display stuff, so not handle that very gracefully. But okay, I think that's probably enough data. We're connected to Wi-Fi, and we'll cancel. And then we're going to do log parser, and we're going to do our Wi-Fi. And then let's come down to our graphs and refresh. Okay, looks a little different, a little more interesting. Some things are up a little bit here, but still not much. But the one thing I want you to notice is all we've done is connect to Wi-Fi using IDF calls, but look how many more threads we have running. These are all things that IDF is doing for you behind the scenes. I never created a thread called timer service or TIT or sysevent or Wi-Fi or ESP timer. Those are all new just from enabling Wi-Fi, a Wi-Fi connection in your project. So you can see those things and how they're using CPU over time. I'm going to sneeze. Excuse me. Okay, and so, but again, not very big on CPU usage, but what we are going to see is a huge difference here on memory. We went before, I can't remember what we were at, 320 something, and now we're down to 250 just from turning on Wi-Fi. Like, you're using a big chunk of memory. And the same thing for all of these tasks, you can see how they're stacking up on stack performance. So Wi-Fi task, lot of free stack space. Now, we haven't done anything with the Wi-Fi, so we haven't tried to really send any data or do a post request or get or anything. So don't just look at this and say, oh, we could reduce, because in menu config, I believe you can change the Wi-Fi stack size. You don't want to just look at this and say, oh, I could probably lower this by like 3K. You need to be running in all of your different like end user scenarios to see how these things are changing over time. Okay, so, pretty interesting. Just turning on Wi-Fi. Same thing with Bluetooth. If you do anything with Bluetooth, you're going to see a whole bunch of new threads come up, where they get on which cores. The thing I do also want to mention about core usage here is, you notice we're stacked heavy on core 0. You can change for many of these. You can change the core they run on. And so if you have a bigger project with a lot of things running, this view really helps you see, maybe I'm overloading one core versus the other and I should move some of my tasks over and things like that. And so now let's talk about memory leaks, because this is the reason I originally made all of this, is because I wanted to see, I suspected we had a memory leak, and I confirmed that with just logging in the output of like what the heap space was, and I saw it going down. But it was kind of like, I got to keep remembering the number and how's it changing. And really, for me, I'm a visual person. I like graphs. And so I made a graph. I could see the memory leak. And then really what I wanted to do was make a code change, build it, run it again, and see that the memory leak was gone on a graph. And so that was when really kind of the power of this was evident to me. So I have this memory leak thread that I've prepared for our stream today. And you can see that all I'm doing is, while true, I'm mallocing a kilobyte. I'm setting it to 0. I'm stir copying into it, and then because the compiler is really helpful. If you just malloc and you didn't have any of this stuff down here, it's going to optimize it out because it knows that you're not using it, and so it does you a solid in that case and saves your bacon. And so this is a way to make sure that the compiler doesn't optimize out my allocation here. So every 2 seconds, I am allocating. Let's change it. Let's go 1 second. Let's be aggressive with it. No, let's do 2 because my stat interval is every 1 second, so I don't want them to fall on the same interval there. Okay, and then all we're going to do is we're going to xtask create our memory leak thread. I'm calling it leak. I'm allocating 2K for the stack and priority 5, and these are just context things that we don't need to worry about. So let's flash that now. And we'll look at a couple of different things here. Okay, we're running, grabbing performance data. We're going to let that run for just a few more seconds while I take a drink. All right, that's probably. Oh wait, I'm not grabbing this. I gotta switch back over to my utils. Okay, let's do a profiler, and let's call this one memory leak. Okay, we're gonna let that run. Let it connect to the Wi-Fi. Let it leak some memory. And then we'll see what we got. I'll let that run for a little bit. Okay, that's probably good enough. Do 5 more seconds. 0. Great. Now let's do our log parser and do memory leak. And then let's go take a look. Okay, so this is before I refresh. This was what we looked like before. Our memory was nice and flat because we weren't doing anything. We just started up Wi-Fi and then we were sitting there. And now let's go ahead and refresh this so it loads the new data. You will see that I have a new task here called leak. And these are, you can turn these off. And so you can just focus on what you want. Okay, so my leak here started reporting. I wonder why it took so long to. It's 15. Oh, it's that's 1.5 seconds into the thing. Yeah, so this is time down here, and so again, yeah, it says uptime in milliseconds. So this is well, 15,000. That'd be 15 seconds. I'm not sure why this came in so late, but you can see that the core usage is very low on that. And another thing I want to look at is the stack usage right here. We declared it at 2K, and you can see it's actually the low watermark. It when it starts up, it uses some amount of resources, and so that's where it's at. And I will change this so you can see this number go way up. And then look what happens right when we start that thread. You can clearly see we got a memory leak here. Our memory is just down into the right, which is not what you want to see. And so this is really powerful when you're trying to look at performance of bigger projects on an ESP32, where you're trying to make sure everything is balanced, and even with internal versus external memory and the performance trade-offs of those. And it's just, like I said, these whatever this is, 1, 2, 3, 4, these 6 panes of charts are extremely helpful for a wide variety of use cases when you're working on an ESP32 project in production. Okay, so let's come back up here and let's do a couple of changes. Let's make our memory leak way worse. Let's go 4096. Let's get aggressive with it. But let's also, oh, and the reason this takes so long is because it's got to connect to Wi-Fi. So let's move where we create this task way up here, so it happens sooner. And then let's give this a lot more, what's, well, I'm not going to do the math in my head. I can't remember the number. 49.6 times 2. Let's make it 8K. And show you that as well. Okay. Yeah, sir, welcome in. We are doing profiling on the ESP32, and I'm just getting ready to show what you would see with a memory leak. Great to have you, man. I hope you're doing super well. Okay, great. And we're not going to sit here and waste our time with this again. We're going to just cancel out of that. And we're going to do profiler, and this one we're going to say max leak. And now, last time I said I didn't know why the task started so late, which again was a piece of information like, hey, why is it taking so long? Well, it was because it was after all of the initialization and the Wi-Fi connection, and that takes some time and retries and things like that. And so now we should see leak as a thread come in much sooner. It's going to have a much higher stack low watermark because we've allocated way too much for it. And then let's do some, maybe AI can write some recursion real quick before we end the stream. But let's let that run for a second, and so we can see the results. We'll go ahead and cancel that out. Good. And then we're going to do our log parser for max leak. And then let's come and take a look at it. Okay, so this is what it looked like before. Remember, leak came in around 15 seconds. The low watermark on the stack wasn't very interesting, and we can see our leak here. Now we've made our leak worse, so we should see a steeper line here, and we should see a lot more headroom on our task. So let me hit F5 to refresh. Yeah, look at that. That thing is just cranking on memory now. That's a bad leak. And now you can see the colors don't stay consistent because the charting library is redrawing and measuring. So now leak, you can see, is red, and it's way up here. The low watermark is very high because we allocated like 8K for it. Okay. Now down here, one of the things you can't measure without impacting, the thing you're measuring, and that is also the case with something like this, although it's not very efficient. But you can see my profiling library is using about 3% CPU, and that will go. I'm going to change that. I'm going to change that to be a faster rate. Let's just change one thing at a time while we're doing this. So let's come in here and let's do it through menu config. .py config. Oops, let's make that bigger so you can see it. Component config. Let's come all the way down to the bottom to deploy the Fleet SDK, profiling settings, and let's change this to every 200 milliseconds. So that's starting to get pretty tight, pretty fast. Because again, depending on what you're trying to profile, you may miss it. If something's happening, within a couple hundred milliseconds and your profiling interval is 1 second, you're going to miss a lot of stuff. And so let's change that down to 200 milliseconds. Save it. And so we'll do that. What else do we want to do? Oh, let's look at this. You'll notice IPC1 has a 1 next to it. Timer service has this weird number, and that's because it's not pinned to a specific core. You can see all of these are pinned to core 0. These aren't this large number, which is not displayed very beautifully, is telling you that these aren't pinned to a certain core. They are core, because you can set, I can't remember what the name of the setting is, but you can choose core 0, 1, or you don't care, in which case the FreeRTOS will decide where it wants to execute that. And so if you don't want that and you want something on the same core, because again, if you're doing something on one core and it needs to talk to something on another core, this IPC starts to come into play where you're going to use CPU transferring data between cores. And so sometimes you might want to pin to one core or the other. And so we could fix this by pinning leak to a core. And so in both cases, I think it was on core 1, but we could just as easily put it on core 0. And you can do that with an xtask create pinned to core, I believe, and then just on the very end, just say I want it on core 0. I think that should build. Let's see what it says. Yeah, I think that's right. So now we should see leak pinned to core 0, and it should get rid of that long 2100 like max int number and just show a 0 instead. Okay. So let's flash that and see what our changes are. In fact, we're just going to flash. We're not going to monitor. Okay. Let's cd into utils, and then let's say log parser faster faster recording. Oops, why didn't I like that? Oh, log, because I did log parser. I need to do profiler. I'm doing the wrong name here. Profiler. What did I say? Faster. Oh, if I could type. There we go. Capturing from device. I'm going to let that go. Now, again, we changed a couple of things. We pinned it to core 0 for the leak, and we're grabbing profiling statistics at a much, much faster rate. And so we'll see the CPU usage of our profiling task go up significantly. And one of the improvements that I want to make here is, again, this is just a very dumb implementation of dumping out serial output. Serial output is incredibly slow. And so it'd be much, much faster to be storing this in some sort of ring buffer and pushing it out or dumping it in batches. I could also do a ton to compress it. It is very human readable, which was also by design so that you could just look at the output and read it. But let's go ahead and do that. Faster perfs. Now let's do log parser on our faster. And come down here. Okay, so remember 3% CPU, and our leak task was on core 1, and it's got this weird number. So now let's see what we get. We get nothing. Was I not recording? Let's look at faster perf. It's not, because I rebuilt and I didn't build it with the right profiling. Let's clean it. Profiling equals 1. I need to pi. Flash. If you do not build with that profiling equals 1, it's not going to include the profiling logic. And so you'll get what we just saw, which is you get nothing. All right, so this should get us there. And let's go ahead and delete our faster perf because it didn't actually have anything. And let's try that again. Okay. And let that boot up. Getting a little short on time. I do want to try and show the stack watermark with some recursion. So, see if we can get that in here. Okay. Now let's do our log parser on our faster. And now let's refresh. There we go. Okay, you can see leak is now on core 0, just like we wanted to. And leak also, you see, now has a 0 instead of this 2-1, unpinned core indicator. I should just change it so that if it sees that number to say unpinned. So anyway, that's an example of how we would do that. You can see that our memory is going down, down, down. But is it really doing every 200 milliseconds? Let's see what our CPU usage is on profiling. It's still at 3. Oh, because it's getting overridden by the profiling default. Okay. By this. So let's, every time we go into that, let's do that. Oops. The workspaces. Go. Big. Great. Now, before we build this, let's create a void. We're just going to create another task here. Yeah, that's not what I want to do. Let's see if Copilot can do this. Let's see. See if Copilot will come in and do it. Yeah, I do want you to do that. Like, write it for me. Yes. But it's not. Yeah. There we go. Okay, so now in here, I'm going to say, yeah, let's just do that. And it should just bail out. So I'm going to take this, I'm going to pin it to core 1 this time, and I'm going to do it after we connect to Wi-Fi. Actually, I'm going to take out connect to Wi-Fi. It is not recursive. You might be seeing the other one. This one is. Fibonacci is calling Fibonacci. Am I missing something? I don't know how much of a delay we're on here, so the comment might have been a little late. Okay, so instead of memory leak thread, we're going to call this recursive example. We're going to call the thread recursion. We're going to give it more of a stack so that we can see it, and we're going to pin it to core 1. Yeah, the new one. Okay, yeah, sorry, Ibrahim. Sorry, the delay got us there. Okay, let's just, first of all, see if this builds. Well, this will tell us if it builds or not. See if we can make it crash. Okay. Okay. And let's run our profiler, and we're going to call this one recursion. And hopefully it doesn't crash. We'll see if it does, though. I'm going to let that run. That should run really, really fast and be done. So let's hit that. And then let's just, before we go through it, we can actually look and see if it does. Oh, yeah, back brace. Recursion should not return. Abort. Retest task should not return. Yeah, so it's just boot looping. Okay, fine. Let's come back here. I thought it was fine. Well, let's just do same thing here. While true. And then we'll put a little standard, this thread sleep for every 5 seconds. We'll run it. Okay, let's give that a shot. Let's delete our recursion here because it didn't work the way we were thinking. This is why I like to do the monitor, so I can see if it's in a boot loop or not. Okay, that looks like it's running. Great. Let's go into utils, and let's do our profiler on recursion. And let that run for a minute. All right, that should be good. And then we're going to do our log parser on recursion. And then let's go take a look and see if we can see anything interesting. Okay, we also decreased the interval to 200 milliseconds. So I'm hoping to see the profiler use a bit more. And it doesn't. It really just uses about 3%, 2%. Like it's like using less. How is that true? Let's take a look. No, it's still doing 1 second. Yeah, it's still doing 1 second check-ins there, so I'm not sure what's going on there. And our recursion shows nothing. So I wonder if the compiler optimized out. We still have our memory leak. If our compiler optimized out the recursion. I have seen that. I actually did this when I was doing my ULP series. I was trying to get recursion, and the compiler was saving me every time, saying, no, that's not how we're going to do that. And so I think, let me try one more thing. We're getting to the end of my time on the stream here. I think the last thing we could try is because we're doing 10, like the compiler knows I know what you're doing here. But what if we did ESP random? I don't know where that's at. And it returns a uint32. Yeah, let's do that. Let's do int or auto no, int r equals ESP random, and then Fibonacci of r modulo 20. And we're going to say r. ESP random was not declared in this scope, and it doesn't have a semicolon. There, yeah, that was it. That was it. Okay, so every 5 seconds we'll be doing a different Fibonacci sequence, and I do want to know why it's not doing the right interval. That is a problem. 200 milliseconds sample interval. I'll have to mess with that later. Okay. Last chance at it. So we can see the stack, or I'm just terrible at it. It's Friday, but we should see the stack decrease, the overhead decrease. What am I looking for here? Profiler. Let's do recursion again. All right, let that off. And see what we get. It was every 5 seconds, so we'll let that run for just a little bit longer. So anyway, I'm going to go ahead and do my wrap up here while we're letting that run. So again, this is just a simple way to do this without buying an expensive tool if you're in a production environment. And it's something that I am actively working on to improve because I think there's a ton of value here. I've used this tool a lot. It is clunky to use, but the general idea here is that you have some things at your disposal that you can do profiling with before you can afford to go up to heavy duty tools. I guess is kind of that's the segment I'm going for here. Is you don't have to start with the most expensive tools on the market to get extremely valuable data in helping you solve problems in your project. And let's see. Now it's just not doing anything. Okay. All right. I don't know how to mess around with that. To see why it's not. See why it's not doing that, and get a better example of the stack watermark. But it will show you if you're going deep into your stack, it does show up on that chart. I guess you're just gonna have to take my word for it. Oops. Let's just do an if.py monitor real quick. Make sure that it's actually. Okay. I'm not seeing the output. Oh, because I don't have the. Yeah, well, whatever. I'm not sure why I'm not seeing this output right here. So I'll mess with that. Anyway, just want to go over kind of a baseline profiling and kind of what information you can see. I'll show the graphs one more time. CPU usage, low watermark, memory statistics, very helpful for working in your projects. Appreciate everybody watching. If you do have suggestions for streams, I'm going to call out again, productionesp32.com/voting. You can vote up any of the ideas I have listed here, or send me ideas. support@productionesp32.com. I'm happy to have stream ideas. I know people have been asking for this build with CI. I'm getting there. I promise I'll do a stream on that. I just want to have a little bit more polish around that. And so, again, appreciate everybody watching. I hope you have an amazing rest of